Welcome back. So we are now at class 5. We're making steady progress. So we have 5 out of certain lectures now. And today we will be talking about estimation procedures. So we have spoken about the interpretation of models. We have spoken about the interpretation of R outputs, and we have spoken about, okay. All right, so that's okay. And we have spoken about the interpretation, we've spoken about coefficients, we've spoken about how it's being built, we've spoken about how to develop regression models. Now we're going to talk about how that actually is fitted arithmetically, right? So as you can imagine, there are various ways how to actually do that. The more common ones we're going to discuss today. So class 5, please create a folder. As usual, please open the RMD file that you have downloaded from the item folder on Blackboard. Copy them in a lecture folder in the class 5 folder and add the 2 JPEGs. The 2 JPEGs are needed because essentially they will be used by the RMD file to mesh and knit together into what will become the PDF that I have built here already. In any case, I'm going to build it again. Okay, so I'm building it right now. In the very same context, I would also like to bring to your attention that homework 1 has posted now. Homework 1 essentially is due on 10/11. So you have 2 weeks time. So you see, I'm recording this on a Saturday, but essentially it will go online on Sunday. It's due on 10/11. It's a simple exercise that shouldn't be too difficult for you to master. You can briefly have a look at it while R is creating the markdown file. What's the one point? Is it the demonstration effect? Whenever you want to show something, it takes forever. So, okay. But let's see, it's doing something. So, okay. So the PDF is getting finished now. And the Word document downloads. It opens up hopefully sometime soon. All right. Because that's still finalizing. So homework 1 essentially is downloaded now in the meanwhile. So essentially here we have homework 1, the outline. So we're seeing now here the model. This model is essentially not scientifically justifiable. However, we have here betas and the p-values. And here we have examples that essentially will ask for you to employ what we have learned over the last 4 lectures. So essentially it's practically employed what you've been taught. And I think this shouldn't be too difficult. It will allow for you to get prepared for the exam. And it's didactically a very valuable exercise. All right, so good luck with this. It's due in 2 weeks from now. And And so let's get started now with the lecture. So we are essentially now looking at lecture 5. Yeah. So let's go to the first one. This slide. Okay, good. So after all this, now let's get right into it without any further ado. Floating pounds. Okay. So applied biostatistics 1, class 5. We are essentially today. Okay, class 5. So we we have briefly looked at homework 1. Homework 1 essentially will allow for you to practice for your exam. And it will make use of the first 5 classes and will test for the knowledge that had been taught over the last 5 classes. Today we will be talking about some aspects that are also part of this exam, as well as the homework, which are the estimation procedures. So we will be discussing today the ordinary least squares method of fitting functions through existing data. And we will further look into maximum likelihood as a method to estimate coefficients in a model. We further will be revisiting R-square. R-square is a marker of the strength of a model. Essentially, it is, as we know, it's the proportion of variance that was possible to be explained by the model, by the fitted model, in comparison to the overall variability of data points. So it's variance of explained data points of the explained part of the data over the overall variability and variance. We will then do lab 5 in a separate lecture, talk about how to empirically approach and prove these equations. Good. Least square estimations. So as you can imagine, these regression coefficients need to be mentioned, need to be estimated based on estimation algorithms to essentially fit this model into the existing data. So exactly, we have here the simple linear regression equation where we have an intercept available. We have here the slope multiplied by the xi, which is an actual data point, an independently measured, perfectly measured independent data point, plus a residual error ei. And this is the uncaptured variability, essentially building the residuals. And then we have yi, which is the essentially independent data point. I ranges now from 1 to n, and essentially n represents the sample size. So an alternate way of looking at this is that we have xi and x and yi. So we have these pairs of data points, and we want to essentially find a function which is here stated as s beta 0, beta 1, because these are our unknown model parameters. In essence, to come to a modeled yi as a function of a modeled beta 0 and a modeled beta 1 that essentially allows for xi to predict yi hat. So the idea here is really that yi hat is as close as yi for all the existing entries, i's, for all i's. So this being said, we essentially were looking at here the scatter of serum glucose, systolic blood pressure, So we essentially see systolic blood pressure as a function of serum glucose. So in a perfect world, we would be able to account and predict every data point that is stated here. So hypothetically, you could just connect all the data points and develop that as a function, which would be a polynomial function at a very, very high level. But hypothetically, it's possible to fit as highly complex functions, but it's not interpretable, it's overfitted, and it basically doesn't make any sense. It doesn't create generally applicable knowledge anymore at this point. So the higher order your function will be, and there are arguments, and you will see this later, there are arguments to essentially fit cubic, quadratic, or cubic functions and go in the realm of nonlinear regression. And you will be exposed to that in further lectures of your education. And you may hypothetically choose to do that. However, the interpretation becomes very, very complicated, and it's not very easily digestible anymore. It's also in terms of usefulness, it also changes. Since we're doing mainly public health research here, it's not very, it's not the most common approach. It's still found and it's still done, and it's for many applications, it's very, very useful, but it's not the most commonly used method to use nonlinear regression. Okay, but in any case, so we're looking here at the association between systolic blood pressure and serum glucose, which is in terms of the magnitude of the values, rather implausible values. But again, this is just for the sake of showing and displaying the associations. And we essentially, what we want to do, we want to fit a function, a linear functions with that essentially presents like this. So it essentially, it is supposed to show an association where yi, the distance between yi hat and yi is as small as possible for all existing entries. So what this essentially means is that we aim to minimize Ri, so the residual of I, so we're minimizing to a maximum, so we're actually minimizing it to as small as possible. So our yi minus yi hat is supposed to be as small as possible. So this is essentially the idea. So now how can we do that to essentially form this as a function? So there are three examples that Professor Seng has stated here in the slide. So we have as the first way of formulating this function, we have so the function of beta 0, beta 1 is the sum of yi minus beta 0 plus beta 1 xi. This, unfortunately, so now when you go back to this equation and to this, you can imagine that there will essentially be not much of a sum, because essentially you have negative ones and you have positive one, and basically it will cancel out over the realm of the entire function. So we need to do something different. So really equation 2 and equation 3 show the alternatives. So one alternative is to basically set this absolute and say that yi minus beta 0 plus beta 1 xi essentially is always positive. So this will essentially create a value that essentially could allow for us to kind of see the difference and work on minimizing that difference by fitting each point respectively. So now another way, and this is better because it's to some extent Professor Seng stated in his lectures, and this is also what I found online. Essentially, there's not that much of a difference between absolute and equation number 3. Both are to some extent functional. So it's if Professor Seng doesn't see the difference, I'm not even gonna go anywhere close to trying to hypothesize about differences. But I think what could be seen as a difference in equation 3 is because you're squaring it. well, first of all, it's the least square method, so squaring it essentially has advantages, and it also has advantages because it amplifies the magnitude of these differences, and as such, essentially, it allows to kind of minimize more efficiently by having a maximization of these differences, and by that, essentially, we can more versatile flexibility of the fitting. So intuitively, both are kind of okay, whereas 3 exaggerates the differences as such will allow for more efficiency in the fitting. So we could now obtain yi hat equals beta 0 hat plus beta 1 hat xi with beta 0 and beta 1. So the idea behind it is that we should be able to so essentially you want to minimize the differences caused between the actual data point and the model fit. As such, you resort to the derivative of your essential equation, and by creating a derivative between beta 0 and the function of beta 0, beta 1, which essentially is this function, we essentially, if this difference, if this ratio equals 0, we have a minimized difference. And this least square method was developed by Adrian Marie Legendre. What that essentially means is exactly this. So let's revisit the history later. So I just want to emphasize and show what this actually means. So the derivative is essentially, so the first derivative essentially is showing the change over a certain magnitude of a parameter. So if this derivative equals 0, that means that's this point of no change at this point in time. So this derivative essentially is here, this dy dx, this ratio is essentially 0 at either the highest point or at the lowest point. In either case, here it is 0 because it is either the maximum or the minimal point of this quadratic function. And the argument that we could be making, and we didn't look for earlier, whether we should use a squared approach or just an absolute approach, the argument here could be made that here the squared approach essentially forms a quadratic function that essentially does have a maximum and a minimum, and as such allows to derive this this partial derivative, essentially allowing to achieve a 0 where this essentially is either at a maximum or a minimum. So this makes sense, right? Because if we take this as an approach, so we're forming this function and we are fitting this to an extent where we have a minimal value that essentially allows for the fit of beta 0 and beta 1. Good. So this is the ordinary least square. So again, we're coming from building this function of beta 0 and beta 1 as the sum of yi beta 0 plus beta 1 xi squared. And we are essentially using this to getting to the solution of the ratio between the derivative, the partial derivative of this function beta 0, beta 1, which is a quadratic function, over beta 0. If this is 0, we are essentially at either the nadir or at the maximum point. And this is true also for beta 1 and can be done for each set of covariates. We'll talk about this in a second. So this is the so-called least square methods, where we essentially mean to minimize the least squares. So this was officially discovered by Adrian Marie Legendre in the early 19th century, and is co-credited to Carl Friedrich Gauss, who we all know from the development and description of the normal curve. So we have seen this slide where we essentially see a minimization of these terms and the minimization of the ratio of the derivatives of beta 0, beta 1, and beta 0. By that, seeing either the highest or the lowest point in this quadratic function, allowing for a fit, minimizing the differences. So if we are solving these now, essentially we can solve this as a beta 1 here as xi minus x bar. So this is our difference between the xi and the mean, yi minus y bar divided by xi minus x bar squared. So this essentially allows us to quantify the mean and the deviation of the respective xi's from the mean, which essentially is a square line, a vertical line, right? So now we have y bar minus beta 1 hat x bar essentially now derives from beta 1, as we have developed it here with xi x bar, yi y bar. So essentially now we get in a last step, we can now essentially solve this to come seeing these scoring equations, and as such we essentially get to a point where we can develop the final equation for all covariates, where we essentially employing this method. So we can do this as for each set of covariates, and it basically results in the same set of scoring equations, allowing for a minimization that essentially will allow to come to the final linear regression equation. As a numerical example, you got to look at this again with the blood pressure. We essentially go back to our individual. So now you can essentially calculate the residuals easily by hand. And this is something that will definitely be important for both homework and exam. So you essentially have x1, you have age. If the age is 73, x2 as not being graduated from high school, or 0 if otherwise. Let's assume 0 here for the sake of argument. And x3 if graduated from high school but not from college, also is 0. We're essentially getting, we can use this equation to literally enter the x values in a way, that's supposed to be 0 here, in a way that we can easily calculate or steps and get one individual data point, which is essentially allowing for an estimated y hat, and then it's really just a difference that needs to be calculated as the so-called residual. An important property of this least square is essentially that the mean of these residuals is 0, and they are normally distributed variables that essentially they will distribute around a mean of 0 in a normal distribution. So this is important because this essentially is one of the main conditions of linear regression. So we have this mean of 0, and we have a normal distribution of these residuals of each individual subject's contribution to the scatter that will distribute around this mean of 0. So the maximal, okay. So I hope this was clear so far. We have now as an alternative way of fitting a linear regression function. We have the so-called maximum likelihood estimation. The maximum likelihood estimation works on xi, yi, where I equals 1 to n, allows the minimization of sum of n, I equals 1 to n. Basically, again, the least square equation. And again, this is what we want to minimize in least square. So a modern simple linear regression is thus specified as beta 0. We have the intercept beta 1, the slope, multiplied by xi. This can be obviously extended for multiple covariates, plus a residual error that essentially is independent and identically distributed over the entire range of magnitudes. It's normally distributed. These residuals are normally distributed around a mean of 0 following a variance of the residuals. So this is equivalent to a normal distribution of beta 0 and beta 1 xi and the residual variance. So alternatively, we can say, and this is now where we're getting closer to the maximal likelihood estimation. So those of you that can remember in introductory statistics, I'm just quickly going to show this. I'm just quickly going to show this, and I put off this Wikipedia page earlier, so that the formula for the normal distribution is essentially is nothing else, and you can easily program this in R, and you can program a normal distribution. So essentially, this is this exponential logarithmic function that essentially includes each x, includes the mean of x and the standard deviation of x, and basically plotting this basically allows you to plot the normal distribution curve. And this is being taken advantage here for the purpose of the maximum likelihood estimation. So essentially the idea here is that you use the knowledge around the distribution of these residuals and your function, so the function and the residuals and the variability of the residuals in that shape that you say, okay, I have now exactly this function that forms a normal distribution. I'm replacing x minus mu divided by the standard deviation by the minimization of my least squares. This is essentially this, and I still divide it by two standard deviation square. So by that, essentially, you get an FYI theta that essentially allows you to get a probability density function of theta, where theta essentially is our least square algorithm. By that, essentially, we're getting to the point that all yi and yn is generated from this function of yi theta 0, where theta 0 is a vector of unknown parameters. So the idea here is now really to use this theta 0, this theta hat, to be as close to theta 0 as much as possible. So, and now you're coming in the realm where you develop a probability function for each of your entries. So you are calculating one probability for each entry, and you're multiplying all probabilities in order to maximizing the probability or likelihood of that function yi theta. So the estimate of theta 0 will then essentially be to find a value of theta, this theta, that maximizes the log likelihood theta. So why the log? Because you need to come from this exponential to basically logarithm to log transform it. So theta 0 allows you to find this value of 0. So you get for a simple linear regression, you get to, so again, now please look first at this equation here. So you have 1 divided by square root of 2 pi sigma squared. So then 2 times pi, the variance, multiplied by exponential the S0. So our S0 of beta 0 and beta 1. And reforming that and log transforming this essentially gets you to this equation, which is notably, again, quite close to the least square method. However, it's different because now we're maximizing likelihoods rather than minimizing differences, right? That makes the difference. Okay. So this is the maximum likelihood estimation method. And this is somewhat as distinction between the least square methods, and both are quite common methods. So now we have, secondly, we have now to talk about the R square. And the R square is a feature of linear regression, particularly in R. Is a feature of linear regression that basically allows to quantify the strength of these associations. And it basically gives you an idea about the model quality and the model accuracy, to what extent the model is actually able to explain the total variability. So essentially it is, per definition, it's the proportion of variability in your data that is being explained by your model. So here with 0.65, we're looking at a fairly good R squared, so that's not terrible. And so there are various ways to quantify that. One essentially is shown here, which essentially shows the squaring of the correlation coefficient, which is possible in simple linear regression only. As soon as you have an additional covariate, do not square them. It's a different way of doing that then, because then you will need your residual standard error, and you will need to quantify the F statistics to get your R squared. So it becomes a different conversation piece. Good. We start by relating the deviation from the sample mean with predicted yi. So yi minus y bar essentially is yi bar hat minus y bar. So this is the predicted yi minus the y bar. So that's the mean, plus a yi minus a yi hat. So essentially, this is then the actual. So this is we're getting here the difference from the actual value minus the mean as the difference between the predicted minus the mean plus yi, so the actual value minus the predicted value. And as a consequence, we can also relate the sum of these. And we will then work on quadratic terms. So we will essentially then work on a quadratic term to allow for us to essentially predict the explained variability over the overall probability. And we will do this hands-on in the lab, and we will try to essentially quantify exactly that. So if we are looking now at this explained variance, so here we have the variance of yi minus y bar squared. So we essentially, the basis of all of these variability is always the difference between the individual data point to the mean, right? We have done this sum of square estimations for the simple linear regression. So essentially we're seeing in correlation, we are essentially quantifying sum of squares. We have sum of squares is being built for the standard deviation, for the correlation, for the linear regression. For the linear regression, it's then in addition used to also quantify the set scores, and from that essentially get from an estimate the slopes. So this is the total sum of squares. If we are now using the yi hat values, we get one yi hat for each individual, for each data entry point. And if we are squaring these deviations, now we get a regression sum of squares. And now going in a third level, so we have now regression sum of squares plus a residual sum of squares. So the RSS is the residual sum of squares, where we have the individual data point minus the predicted data point. So it's essentially so total sum of squares is yi minus y bar. So this is the individual data point minus the mean. Then we have regression predicted sum of squares, which is the yi bar, so the predicted data point minus the mean. And then we have sum of squares of the residuals, which is essentially individual data point minus the yi hat. So the total sum of squares is essentially both of these. The total sum of squares essentially represents the sum of the regression sum of squares and the residual sum of squares. So if we're dividing now this on both sides, as we know from the sum of squares, we essentially were getting now variances, right? Sum of squares, remember the standard deviation. Standard deviation is we're building the deviation, which is the individual data point subtracted from the mean. These deviations are being squared. These squared deviations are being summed, becomes the sum of squares. Dividing the sum of squares by the n gets you to the variance. So we have here variance of y, which is our total sum of squares. Then we have a variance of y hat, which is our regression sum of squares. And then we have a variance of e, which is our residual error. So now we said R square is the proportion of explained variance in relationship to the overall variance. So the variance of y hat divided by the variance of y is the proportion of total variance explained by y hat. Good. So this was the lecture for today. And now, so this is a quick overview over the lab. So essentially we're fitting a regression with only one covariate, either by simulation or real data. We're fitting a linear regression model to obtain the regression coefficient by using LM. Then we will manually calculate the coefficient using the formula below and compare them with the model's output. We're calculating the left-hand side of following equation to see if the resulting numerical value is close to 0. So we will do that next. All right, good. So see you in the lab.